Okay. Hello to everyone. Thanks for coming. It's a pleasure to have here Professor Paraskevas. I will spend a minute introducing him because he surely deserves it. So Professor Sphicas holds a PhD in physics from MIT, where he actually became professor very early in his career. He later joined CERN as a principal scientist, and also, since a few years, is also professor at the University of Athens. Paraskevas is, I'm not ashamed of saying that he's a prominent figure in high energy physics, and he actually took leading roles in several measurements and discoveries of paramount importance, among which the discovery of the Higgs boson in 2012 with the CMS experiment. Currently, Professor Sphicas is the chair of ECFA, and for those who do not know what ECFA is a body, is a commission for, it's a European Commission for Future Accelerators. And as such, is one of the organizers, the leading figures in the European strategy for particle physics, which is actually the subject of the talk of today. So now I have actually a personal note. Professor Sphicas will discuss several of the challenges that are ahead of us in the field of particle physics. And as you know, these things requires large scientific infrastructures, important investments, worldwide efforts. So especially when you're young, you really need to be motivated to tackle those challenges, okay? And let's say the personal note is that when I was young and I joined the CMS experiment, together with the other postdocs and PhD students, I had the luck to have bright, inspiring senior scientists, and Paris was for sure one of them. And he, together with the other senior scientists, gave us the motivation and the enthusiasm to achieve what we later achieved. So I'm sure that today you're going to be inspired by Professor Sphicas. Enjoy.
So, good afternoon, everyone. First and foremost, I'd like to thank Marco for this incredible introduction, which beats the #1 rule of a good talk, which is not to have high expectations from it. But okay, we'll try to put that aside. It is actually my pleasure, and it's my honor to be here today and to present what we are proposing as the future for high energy physics in Europe. But because Europe is basically the leading continent in particle physics, by definition, it also means for the rest of the world. So let me start by something that you've all seen a million times, by giving it to you for one more time, which is the marriage of relativity and quantum mechanics has given us quantum field theories. And the standard model of particle physics is basically that. It has three forces that we know about: electromagnetism, weak force, and the strong force. And they have their own carriers: the photon, the W and Z bosons, and the gluon. Actually, the photon and the Z are linear combinations of the fundamental fields, but roughly speaking, this is the picture. The subjects of the force are basically the fermions. So you could have had, basically, you could have gotten away with having a UD quark, an electron and its neutrino. There's a mystery that nature decided to go to the photocopier and make 2 more copies at higher mass, if you want, on heavier paper, making the charm, the strange, and so on, the top and bottom quarks. Nobody understands why this has, it decided to do so. As for how the forces are mediated, you have these nice schematics here, you know, the exchange of a photon, the exchange of a W or a Z, or a gluon between quarks is basically what gives us the interactions. This theory, it's really unfortunate that it's called the standard model. It should be called the standard theory, because that's what it is. It's an incredibly successful theory. It's been tested to a very, very high precision in electron-positron collisions at CERN, at LEP. It has predicted, it actually gives the moment of the muon to incredible precision. This number that you see here on the top right is multiplied by 10 to the 9th. It's a precision which is incredible. This is the experimental value, and this is the most recent result from the lattice compared to it. And then there is 1 million measurements at the LHC that are spot on with respect to the theory predictions. You're not supposed to read anything on that thing just to get the impression that basically prediction and numbers come out the same. The missing link, that Higgs boson that you've all known about, was discovered in 2012. It was a monumental discovery. Okay, we saw it decaying into 2 photons, as you see here, and this is the invariant mass of the 2 photons, and you have a peak. And at the same mass at 126, it looked like at the time, it turned out it was 125. There was a corresponding peak in H going to ZZ events, giving 4 leptons, as in here from the Atlas experiment, and you have a corresponding peak right here. And thus, the Higgs was born. Very quickly, LHC established also that it decayed to tau, it decays to B's, and it also couples to the top. So really, very quickly, the picture emerged that this thing smelled, looked, behaved like a Higgs boson. And of course, immediately after that, this is another plot where you're not supposed to see anything other than be left by an impression. These are searches for new physics at the LHC. And every one of those bars corresponds to basically a limit, because we haven't seen anything. So, and this is on the horizontal axis is a mass, and each one of those objects here is a different search for a different type of new particle, and they've come out short. In summary, we've looked for a lot of possible new things. Nothing has turned up yet. Still, of course, we're looking intensively, and that's where we are. So then, with the discovery of the Brautingler-Higgs boson, which is the ultimate crown in the standard theory, we believe we understand the physics of 100 GeV, maybe of 1,000 GeV, 1,000 times a proton mass. And we should be happy. In fact, at this point, we are approaching where we were many, many years ago, when we thought that everything was complete in our picture. No lesser a man than Lord Kelvin, back in 1900, said that there's nothing new to be discovered in physics now. All that remains is more and more precise measurement. 5 years later, we had relativity, and in 1920, we had quantum mechanics. I will not comment on the Lord's statement. So, let's talk first of all a little bit about the potentially deep meaning of potentially null results. So the first one is that actually the mystery deepens when you don't find things, when you don't measure things, which is, let's think of the Michelson-Morley experiment and what it actually meant in terms of relativity. But let's get closer to particle physics. Rare kaon decays. The K long, the second mass eigenstate of the neutral kaons, should have a very high rate for decaying into mu plus and mu minus. And actually, experiments were looking for it for a long time, but they couldn't find it. It turns out the decay was very, very rare. And sure enough, theory comes in and says, well, if you look at the type of diagram that would be mitigated through this, what you would get is that something would go arise at the scale of something like 3 to 4 GeV squared, and thus was the charm quark predicted. So the lack of a decay or a very, very rare process is actually equivalent to predicting the existence of a particle which at that point was unthinkable. We had 3 quarks. B0 and B0 bar mixing, this is the mixing between the 2 neutral B mesons, led that when it was found, it turned out that it implied that the top quark was heavy. We knew there had to be a top quark by analogy with a charm, but this phenomenon actually led to that. So quantum loops, which you see over here, because these are basically quantum loops, correspond to corrections, higher order phenomena. At the end of the day, rare phenomena, even if BB bar mixing is actually large, and eventually much more information about high mass scales. The discovery of CP violation, when it was found that the K long decays into 2 pions. Up until then, we knew about it decaying to pi plus, pi minus, pi 0. And here's the monumental discovery in 1964. This is a phenomenon that occurs at 2 per mil. That's the branching fraction. Now, what are the implications? We learned that matter and antimatter do not behave the same way. This is what I call one of the biggest results in the history of physics. Because matter and antimatter, we know that, well, they are supposed to be symmetric up until the weak interaction came in. Taking it further, electroweak precision observables and the power of the loop. If one takes just a gamma that's traveling through space but then gets corrections from fermion and antifermion loops, or it gets a Higgs and Zs, or if we look at the decays of a Z particle and so on, all of these loops are actually calculable. And so much so that back in the 1990s, LEP came up with a value for the top quark, which was, after having something like 8 million Zs, which was remarkably close to the actual direct discovery that we had at the Tevatron with the CDF and D0 experiments. We found it at 175, actually 175, the other experiment 180, and it was within the error, spot on with the LEP value. So there's a lot of value in precision and in rare phenomena. Here's another example, not from particle physics. This is the first sighting from Kobe. They're the first ones who actually managed to see these tiny, tiny fluctuations in the temperature. The universe is at 2.7 degrees Kelvin. And then you look at fluctuations which are 10 to the minus 5 that, and look at the wealth of information that was created since then. And then Kobe had the 7-degree angular resolution. Then WMAP came in and had the 0.2 degree angular resolution. And it gave us this picture over here. And what did we learn from that? Well, the age of the universe, really unimportant things like the age of the universe, the dark matter density in the universe, the scalar spectral index, which is right below 1, which is what is needed by inflation, and so on and so on and so on. So there is a huge value in actually honing in and making that picture more and more precise. Going back to the Higgs boson, the new boson at 125 GeV. Studying it, the angular distribution of its decay products, 2 Zs and then going into 2 leptons, one can measure its spin. It has no spin, it spins 0. It is not the God particle, it's the vacuum particle. This is the true name that it should have been given. Amazingly enough also, it is the first force that we know which is non-universal. It is the only particle that does not couple the same way to the different generations. Z bosons don't see the difference between EE and mu mu and tau tau. All the gauge bosons, they couple the same way to all of them. The only one that knows the difference between the different generations, the photocopies that we talked about, is the Higgs. And then the combination of it being 0 plus in terms of quantum numbers, it has the quantum numbers of the vacuum. It's the only particle that can be created alone. Anything else you have to make in pairs, okay? Even a Z0, which is neutral, to conserve angular momentum, you cannot make a single Z0 unless you prepare the initial state properly. Beyond all reasonable doubt, what has been found is a Higgs boson. It is a new kind of force with non-universal couplings. It's a particle like no other. If you look at the Standard Model, one final word on that, it's actually what we call a conformal field theory. You write down the Lagrangian density. There are no units anywhere. There are no centimeters, there are no grams, nothing in there, except in the Higgs potential, where there is one parameter, the so-called vacuum expectation value. It's this magic thing in the Higgs potential that gives the symmetry breaking. It's a magic number at 246 GeV. If you were to take all the momenta and multiply them by a number lambda, you wouldn't see the difference, except for this 246 GeV, that would see the difference. So there's something magic which is only present there. Let me repeat it. It's the only element that differentiates between a top quark, a C quark, a U quark. And lastly, it is intimately connected to baryogenesis. In fact, the shape of the Higgs potential, and there are two ways that the Higgs potential could go from the symmetric state that it would have a very high temperatures as the universe cooled into having the minimum of the Higgs potential. One would be a smooth transition. One would be a first order transition or a second order transition. Second order transition is a smooth one. Now, this is actually intimately connected to understanding, again, the matter-antimatter asymmetry in the universe. Remember Zakharov's three conditions in order to get the matter-antimatter asymmetry. You need baryon number violation, right? You need CP violation. And the third one, you need to be away from thermal equilibrium. And the only way you can achieve that is not via a smooth transition, but by having bubbles, right? And at the wall of the bubbles, you're out of thermal equilibrium. We need that type of first-order phase transition if electroweak physics is going to explain how we ended up with where we are right now. And lastly, there is a magic of the quantum corrections. The Higgs is actually not protected against those quantum corrections, that if you look at its mass and what it receives from fermions and what it receives from its own self and so on, its mass is runaway. To put it graphically, and these are fake numbers over here, this thing would run amok up until you get to the Planck scale, to gravity, to 10 to the 18. So there would have to be a magic cancellation between a number that they would have to have dialed at the central offices of the universe and all of these quantum corrections, so that this 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, I just put enough digits here to subtract two numbers that give exactly 125 GeV squared. This would be an immense coincidence of googly sizes, just incredible. Or there's physics behind it. And we have previous examples of that, where there's physics that actually tames what would have been infinities. The electron self-energies, where the introduction of the positron to first order cancels the first order corrections that would run away as the energy scale. Or the rho mass, which you can predict by looking at the mass difference between the pi plus, pi minus, and the pi zero. And that gives you that something around 800 MeV, the rho mass, explains that, and essentially pi-pi scattering and the strong resonance. Where do we stand today? The Standard Model is either incomplete or simply an effective theory of some ultimate theory. We have the mystery of the Higgs boson. We have the electroweak hierarchy problem. It's this issue of the Higgs runaway mass. The flavor puzzle. Why 3 generations? Why is nature non-minimal? Okay? And then on top of that, we obviously have neutrino masses, which to this day we don't understand. They're 1 million times smaller than those of the electron and so on. Dark matter, we'll talk about the mystery. And of course, matter-antimatter asymmetry and so on. Plenty of questions that probably would make Lord Kelvin think about it again. In this context, we have the 2026 update of the European Strategy for Particle Physics. This is a cornerstone of Europe's process via which we decide what it is that we should be doing now, but also for the next 20 years and 40 years and so on. The motivation for the most recent update has been basically the results from the LHC, the completion of the FCC, the Future Circular Collider feasibility study. That was a major step. And of course, the international landscape. China started planning similar facilities. The US completed their big review, happens every 5 to 7 years, and so on. The aim of this is to create, let me quote from the charge that we got, a visionary and concrete plan that greatly advances human knowledge in fundamental physics through the realization of the next CERN flagship project. Now, what that means is that the strategy should include the preferred option for the next collider at CERN, prioritized alternative options to be pursued if the preferred plan turns out not to be feasible, and also other areas of explorations complementary to that. It's important to note that the European strategy develops recommendations. At the end of the day, the money holders, the project approvers, are CERN Council. This is a process that lasted a long time. It was launched essentially at the end of 2024. 3 months later, there was a deadline to get the submissions. We got 266 submissions, and it ran through with a big symposium right next door in Venice in June of 25, a long process of various milestones and so on, and we're right here a week before the final announcement to the world. Hopefully, CERN Council will adopt it. It involved a lot of people. And when I say these are just the 600 people or so who showed up in Venice, there were many more connected on Zoom and many, many, many more who have contributed through all of these hundreds of contributions. This is another picture that's supposed to show you that there were a lot of people. Now, let's talk about the enablers. This is really where the power comes from. As Freeman Dyson said, new directions in science are launched by new tools much more often than new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. So, the enablers are, first of all, the Future Circular Collider, a new machine like the LHC, this time around 90 kilometers long and in the same place at CERN. The other possibility would be a linear collider facility. Electron-positron, again, it would take something like 30 kilometers. Another design for a linear collider, or intermediate projects where one would speak of reusing the LHC tunnel, putting back electron-positrons and achieving much higher luminosity, much higher intensity, or the LHEC, which is to have electron-hadron collisions in the LHC tunnel. For the very long term, though initially considered also for the short term, was a muon collider. This would be stage one. When you make such a grand facility, you also have to think about where you're heading after that. So the grand what's the real goal? We would like to get to an order of magnitude higher energies. We would like to see the next layer in nature's onion, right? So the natural sequence would be if you have an electron-positron collider in this 91-kilometer tunnel, many years later you would put a hadron machine, making the FCC HH. If you were to not build it and just stay with the current LHC, your most natural path would be to also go there, but then you don't have the tunnel for free. Another possibility would be that you go for a muon collider. This is a very exciting technology. On the other hand, it's very difficult. We've never had beams right now, colliding beams with unstable particles. This raises a whole new set of issues. When solved, it will be an incredible new thing. But for the time being, there's a lot of R&D to be done. And then eventually, what about if you had the linear collider? Well, what you would hope for is some kind of major advance like plasma wave acceleration to yield, gigantic accelerating fields and so on, in order to get you to the 10 TeV limit. But again, that has huge technological challenges. First of all, it's not easy with a driver beam to accelerate positrons because, well, the driver beam, you don't have enough positive charges. You can only do it for negatives, which is why people are looking at lasers and so on. It's basically technologically challenging. Much more information if you want in the questions. The strategy was a long process. There was a physics potential. I will concentrate on that today. There was a project assessment, timescales, the level of definition, the level of R&D which is needed by each one of these machines and so on, and also input from the national HEP communities. They were given specific questions to answer, and they all answered back, and we had to build the statistics. And the other element that we put in there is, what's the potential for not stopping at the next machine, but having a very long-term future to get to the 10++ TeV part on center of mass scale. This is what was all combined into the outcome. Okay, so let's talk physics. Enough bureaucracy. What's the first thing that one wants to do? Well, you want to probe the Higgs, right? With higher precision. I hope I gave enough motivation for studying the Higgs with precision. The first thing you do is you say, I will look at its decays, and I will look at the branching fraction. For the Higgs to go into F, well, actually it would be created by some initial state, and so on. So you would look for modifiers in the couplings, in the coupling of the Higgs to the initial state, and then the coupling of the Higgs to the final state. So then that translates into what can you expect from the machine that we know we will have, which is a high luminosity LHC. At the end of it, in 2041, meaning in some 15 years from now, what will we have? And well, here is the result, the combination, the expected combination from ATLAS and CMS. The couplings to the photon, the W and the Z would be known to better than 2%, but we're still talking percents here, okay? To top, bottom, taus, somewhere in the range 2 to 4%, and the more rare decays like muons or Z gamma, they would be somewhere in 3 and 7%. Let me assure you that this study has been carried out for each and every collider. If there's some message to take from here, you see the little blue, which is always lower than anything else. So the little blue that you see here is always a combination of the FCC-EE and the FCC-HH when you run the whole integrated program. What's the major thing that we found out through the process? That actually, to understand the nature of the Higgs field, it is not sufficient to analyze the properties of the Higgs particle. You actually have to tackle it from all sides. You have to explore all phenomena. So the first one is W and Z masses with the highest possible precision. The other one is the Higgs self-interaction itself, which is what gives the shape of the potential. And lastly, flavor. There's a lot of physics in flavor there. And it's only the combination of the three that gives you the biggest reach in physics. You cannot just go straight after the Higgs. You have to cover the whole thing. I will show you. Now, of course, we don't know what the new physics is. There's many models out there, but we don't know what it is. What we do know is about the Lagrangian of the standard model as we have it, which is, we believe, just the tip of the iceberg. And above the sea level, we have the renormalizable dimension 4 interactions. This is the Lagrangian density, so it goes d4x. So therefore, it's 1 over centimeters to the 4th, which is why you have to have up to 4 GeVs here. So you have the interaction of the gauge bosons, you have the Higgs with 4 of them, or you have the Higgs going into 2 fermionic fields. Underneath that, there is probably, most likely, for all the reasons that I told you, an entire iceberg. Now, we have to parameterize this iceberg, and this is done by introducing now higher dimension operators. This is getting a little technical. Bear with me for a moment. And for the particle physicists here, actually, there are 59 electroweak structures, almost 2,500 different parameters that one can put in if each and every one of those has a different parameter. you can assume some basic flavor symmetry saying that only the third generation is special, the other two are sort of similar to each other. Assume also CP conservation, you can bring the numbers down. A full effective field theory analysis has been run on all the expected results that we have, and it gave this. There's a lot of work that's gone into doing this. Let me summarize it in a more palatable way. Here are the different machines that we could have had, that we could have chosen. Now, what you see here is the precision physics and the discovery physics, the beyond the standard model. The higher, the better, first of all, in these graphs. Second, it's what you can get after they start operating at 10 years, 15 years, and eventually when you get to the full FCC-EE plus HH. Two things stand out very quickly, is that this is by far the best program in the precision, where you get all fives, in fact, for Higgs, the different colors are Higgs, electroweak precision observables, top, flavor, QCD precision results, quantum chromodynamics. And then the next one here is FCC-EE. And it's actually much better than all the other alternatives that we studied. And the same thing holds true for physics beyond the standard model. Now you tell me these are random bars, so can you say something more? We had to somehow show the world what you actually learn or you not learn by having alternative machines. So what you see here now is this Rolodex, is this rosette plot, where in each one of these pizza slices, you have a different type of physics. So right here, you have the Higgs self-coupling, Higgs-only operators. Or here, you have the quark-Yukawa couplings, where you add an extra, because now we're looking at lambda to the 6 with dimension 6 operators and so on. And you go around with top operators, Higgs operators, electroweak, trying to cover basically the whole scenario for what could possibly show up through this effective field theory analysis. And then what one does is that one then chops it up from the outer to the innermost, chopping it into sub-measurements inside. And when you don't learn anything more beyond the high luminosity LHC, you paint it black. When you learn little, you dark shade gray, light gray, or when you learn it all that there is, well, you learn to the white that you see here. On the left is the FCC-EE. It would take us, after the high luminosity LHC, from something that would be all black, it would be the knowledge of the high luminosity LHC, to what you see on the top left. On the right is what happens when you supplement it with a hadron collider after that. The scale is logarithmic, with a high luminosity LHC being 1 and the best collider option being 5. It's a relative scale. This is a competition. Now, you don't need me to tell you that you see a lot more black, a lot more dark shade here, and we can go on for hours. We need 5 colloquia. I can stay in Padova. It's actually a very pleasant place to explain each and every one of these pizza slices. But the impression that you get from this is clear. This is a linear collider of 550, click another linear collider option at 1500, and this is the FCC-EE, the first stage. This is the first stage, the ultimate stage of the linear colliders, I apologize. And this is the first stage EE colliders, where it's even darker, as you can see here. There's basically no question about it. And then if you ask the world, if you ask all the countries, all the physicists, what do you think is the preferred collider? Well, we have basically a nearly unanimous. One country said the muon collider, and that was because they probably thought that it would be the second option that would be chosen. Well, second option, they put FCC-EE, but everybody said the FCC-EE, the future circular collider, E plus E minus collider. With this, we arrive at the preferred next flagship collider, the FCC-EE. It would operate at 4 different energies, basically on the Z pole. This is time. This is the luminosity that one accumulates on the Z pole, the 2W threshold, ZH. This would be the little Z factor if you want, and at the top, the TT bar. The strength of it comes in the luminosity, in the numbers. One can say that Z and WW were already seen at LEP. Well, yeah. The exception is that the difference that the FCCEE now will give data samples that are 10 to the 5th times higher than LEP. We will accumulate in 3 minutes all the data that LEP accumulated in its years of running of the Z peak. This is the luminosity, this is the FCCEE, this is what the linear collider looks like. So at the Z peak, there's a difference of 1,000. And this statistics makes a difference because, like we said earlier, you need the flavor physics, the electroweak precision observables, and the Higgs measurements to corner the new physics from all angles. So it would deliver the world's broadest high-precision particle physics program. It has an outstanding discovery potential through the Higgs, the electroweak, the flavor, the top sectors. It has technical feasibility that has been demonstrated. And lastly, the scope and the costs are actually very well defined because they've been studied through this feasibility study, and there's even plausible funding models. It would maintain Europe at the helm of particle physics worldwide, and it would pave the way towards a hadron collider that would eventually operate at 100 TeV, let's say one day, 85 to 100 TeV, to push us beyond the 10 TeV parton center of mass scale. Who can ask for anything more? Let me give you some examples. Talk about luminosity and what it gives you in terms of unprecedented precision. Today, the error on the mass of the Z is at 2,000. The units here are kilo electron volts. The FCCEE would turn the 2,000 into the number 4. Error on the width of the Z, the 2,300 would make it a 4. The error on the muons, the error on the Bs, they would go from a few thousands down to single units. No comparison to basically a linear collider over here. LEP3 would have quite high intensity. It would get close, but not quite there. Graphically, if one does the big fit in the standard model of mass top and mass W, this is what happens from the theory fit. This is currently the experimental result, the dashed line over here. In the future, with the knowledge, with the measurements that we will have from the FCCEE, this line, this wide range that you see here would actually shrink into this little area here that one has to zoom in. As for the experiment is right here. You can actually see this little size. So if things were to stay at the same central value, you would see a deviation, a clear deviation from the theory prediction. You can also look at it in terms of the S and T variables and so on. This is there for completeness. Let's talk flavor. Let's talk charged lepton flavor violation like tau decaying into a mu gamma that you see here. And this would be the ultimate measurement. This is a branching fraction. So it would get us even beyond the current B factories that they would operate. Okay? Or branching fraction for tau going into 3 mu. You gain almost an order of magnitude better access, and much, much more that I wish I had time for. What about the hierarchy problem that we talked about? Would you be able to probe it? Remember we said that you need the lowest Higgs max that somebody dialed at the central office of the universe, the quantum corrections. There are 2 main options for remaining with a quasi-natural solution, a composite Higgs, if it's made out of 2 particles, or SUSY, supersymmetry. What would you reach? Well, here it is. What you would cover with the new machines, this is essentially the trilinear coupling of the stop quark, the top quark patterns in SUSY. What you should get from this is that the new machines would allow us to probe all the way to here, okay, FCCHH, and cover all of this space. This is where the minimal supersymmetric standard model is compatible with a measured Higgs mass. As for what type of reach would you have with the ultimate program, the FCC-HH, in terms of new particles? What you would get to is from these lines that you see here, these are TeVs, you would get to masses of 10 TeV here for squarks. For light squarks, you would get to above 10 TeV, and then for gluinos, you would start reaching the 15 TeV scale. These pink lines are way off scale with respect to anything we have today. What about the Higgs self-coupling? We said that the Higgs shape is very, very important. Already it's a miracle, and I'll come back to this, that the HLLHC will deliver this type of precision. Now, this is a precision on the self-coupling, and if you look at the first stage machines, including the FCC-EE, the precision will stay around 25 to 28%. But when you build the ultimate machine and you connect it to the FCC-EE by having direct HH production, you would drop down to 5% on the error. This is the shape of the Higgs potential, and the gray is the uncertainty, as we know it pretty much today. This is from Gavin Salam. The universe basically lives right here at the minimum. In the 2040, after the high luminosity LHC, we will basically know it roughly like this. This is with the FCC-EE, there's some improvement, and this is what you get with a combination of the electron machine and the hadron machine. And now you know whether this is a first order transition, whether electroweak theory and electroweak baryogenesis can explain the universe. Of course, there is always a question of what happens if you cannot get this ultimate machine. What's your plan B? We considered all other collider options, not the FCC-EE, as potential alternatives. And basically we found out that all of these alternatives do not present a concrete and visionary plan, which is what we were asked to do, by failing on one or more of the requirements for the next flagship collider. The first one is to have sufficient precision in the electron-positron step so as to be competitive with a corresponding machine running concurrently. This is code speak for basically the circular electron-positron collider in China, which China, right before the strategy started, sent us a letter that said the project is not approved in China right now. If you, Europe, approve the FCC-EE, we shall come and join you. However, if you do not approve it by 2030, which is the next 5-year cycle in China, we will pursue it again. So if Europe doesn't do it, China will do it. And we don't want to run an inferior machine. The other one, the second requirement, is to provide a sufficiently concrete plan due to pending demonstrations of key technology elements. As I told you, it is not clear right now where we can get to with plasma wake field acceleration. It's promising, but it's quite far with respect to where we are today. And the last thing is a convincing vision for exploration of the highest achievable energies. How would you do it? With another tunnel? Building 2 tunnels in the Geneva area is probably going to be extremely difficult, if not impossible. So, given this analysis and the coherence of the input from the national HEP communities, we considered the possibility of basically just downscoping the FCC-EE. That would mean reduced physics, okay? On the other hand, if more funds would be available, if the US, if China, if Japan, Canada were to come in and contribute, we could restore the full program as long as we would have the big tunnel and the basic machine there. So there's a descope scenario that's been found. One is to remove the top core crown. This is the easiest one because you don't do the final upgrade of 1.3 billion. You do 2 experiments instead of 4. That would bite you when you come to the Hadron Collider. You really want the 4 experiments. You reduce the RF power. Make a long story short, we save about something like 2.5 billion on the total price. Does it hurt? Yes, it hurts to do this plan B. Remind you, this is the FCCEE. Again, just impression of how much you see, how much clarity. This would be the descoped one. This would be a linear collider running at 250, which would be the main competitor. And again, you see that this picture on the top right is better than the picture on the bottom right. So given the fact that we would maintain a very strong physics program, a viable path, because you have the tunnel, you just remove the machine and you put then an HH machine afterwards, you have a viable path towards 10++ TV. And should additional resources appear, which we hope they will, it will not just be Europe, that you can do away with the descope, we went for FCCEE descoped as plan B. This is the combination of engineering, finances, physics, and the path to 10 TV. Green is good, red is bad, in case there is any doubt. So at the very top, you have the FCCEE. It scores out of a possible 25, the precision physics 22, and the BSM physics 23. Competition via a machine in China, green. Technical readiness demonstrated. It's a bad construction cost at 15.3 if you account for everything. Time scale from 2046 to 2060, roughly, and a clear path to 10++ TV. The descoped one, it hurts. Look at the drop from, you get, these are, I can talk ad infinitum at how these numbers we came up with, but just take the number value for what it is. You drop to 15, 17 in the discovery. Is it its way of saying I spoke too much? Okay, so let me accelerate before we get cut off. You save a little bit of money, you go in the orange. But the linear colliders, they're the same cost at much lower physics performance. As for first stage linear colliders, the physics is nowhere near. In fact, LEP3, physics-wise, achieves more because of the higher luminosities of a circular collider than a linear collider at 250 GeV or 380. The picture is clear. It speaks for itself. So this is plan A, this is plan B. Why is it red for the path to 10 TV? Because it's either technologically not demonstrated or because in addition you need to build the tunnel. Again, this 15 billion gives you a 9 billion channel for tunnel for free for the next machine. It's already there. For the other machines, you have to build something afresh. So there is savings in that 15. Conclusion. The EE Future Circular Collider is recommended as a preferred option of the next flagship collider at CERN, and the descoped FCC is a preferred alternative option. We haven't ranked the rest of them because we don't know what the new boundary conditions will be. And this thing, next week, on May 22nd, in fact, is the final meeting to put the seal of approval by Council on this. Let me give you a few highlights, very, very few from some other recommendations. Our highest priority, and also in the strategy, remains the completion of the high luminosity LHC. In fact, the first recommendation is that the full exploitation of the physics potential of the LHC and the high luminosity LHC, the completion of the high luminosity upgrade remain the highest priorities of European particle physics. Let me get back to this and remind you of where we are. Look at this picture, and let's concentrate now on these error bars. You see the experimental one, the statistical one is the blue. The experimental systematic uncertainty is right here, the green, and the red is actually theory. In all the measurements, the biggest uncertainty is actually theory. Now, in theory, things are are the same as in practice, but in practice, things are different than in theory, as you know. So we are confident that with enough investment in theory, we can expect these error bars to shrink and to get to the level where theory and experiment are again at an interplay. After all, these numbers will be there in 2041, the error bars from the experiment. They're not there today. They're for the high luminosity LHC. So every effort has to be made to complete the HLLHC upgrade with a current schedule. The other thing, very importantly, please don't get the impression that it's all been said and done. There's huge room for ingenuity already now in the physics that we're planning at the LHC and the high luminosity LHC. Let me give you an example from the Higgs to CC bar search on CMS. The deployment of AI techniques, machine learning, and so on. This is a graph neural net that gave us what we call particle net, which is a new algorithm. It has given us a factor 6, which you don't get from the luminosity ratio you expect from the high luminosity LHC to the LHC. All of that because of a technique, a new technique, an AI technique. And this is something that happened in the last 3 years. And already we have the next set of results which are even better. To put it in perspective, this is the expected error with respect to 1. At 1, you see the H going to CC bar. This would be seeing the Higgs going to the second generation quark. Okay? This would be very important to make sure that the second generation feels the Higgs the way the third generation does, the top and the bottom. So, right here is the measurement that you have already now with CMS. This is what we would have expected with the high luminosity LHC at the end of it in the absence of these creative new tagging algorithms for bottom and charm tagging. We basically achieved it right here. And this is basically feeding, this type of development is also feeding this incredible result that at the high luminosity LHC, we expect to measure the Higgs self-coupling to 28%. And it's up to the new generation, to the young minds, who can push this even further to get it down to less than 25% and closer to 20%. There's plenty of glorious room right now for more ingenuity. Other research directions, European contributions to both accelerator-based and non-accelerator neutrino and dark matter experiments are essential and should be supported. This is the understatement of the day. You know about the mysteries of neutrinos. You know about the fact that there exists dark matter, and we have no idea what it is. The difference, of course, is that the main neutrino oscillation experiments are not in Europe, but there's heavy participation from Europe, and Padova is, one of the big players in that. This is an effort that we very much hope that will continue and will be supported. And along with it, there's things like the neutrino platform at CERN and the ecosystem of European particle physics labs. Just to put it in perspective, what are the main frontiers for the neutrinos? We have the 2 long baseline neutrino experiments. I am sure that this has been covered many times, given that you have a group in Padova, the Dune experiment, the Hyper-K experiment. There's a big question of the ordering of the neutrinos, where they're normal ordering. In other words, whether the 3 mass eigenstates, they go from the lighter to the top one is what you would expect, or you have an inverted hierarchy, so M1, M2, or 3, or that the linear combination of E, mu, and tau is the other way around with respect to the quarks, the mystery of the neutrino masses, and much, much more in dark matter. I don't have time to discuss them. It would be beautiful to have time for that, but now you have a reason to re-invite me, and I can enjoy Padova again. Summary. There is a very clear and strong message from the European strategy update. All efforts, Council, CERN management, should be made to make the FCC a reality. It would deliver the world's broadest, high-precision particle physics program. There is an outstanding discovery potential through the Higgs, electroweak, flavor, and top sectors, and advances in QCD. Feasibility is demonstrated, the scope and costs are well defined, and there are plausible funding models. It would pave the way towards a 10 plus parton center of mass scale. We have to support the successful completion of the HLLHC, and over the next 5 years, we have a lot of hard work to do in order to reap the benefits of those incredible luminosities and the beautiful physics that will come out of it. There's still a lot of ingenuity to come up with, to invest into the high luminosity LHC. And of course, we have to continue the accelerator-based and non-accelerator neutrino and dark matter experiments because, well, they are frontiers that probe probably the same physics essentially one day when we find out what is behind the Higgs or beyond the Higgs or with the Higgs, to be seen. So that's basically what we're suggesting as a plan for now. Thank you. Sorry, I took longer.
No, that was okay. Thank you very much, Paris. There is, of course, time for questions, and I would give priorities to students, given the fact that they are the one concerned with this long-term program, right? So, I mean, please don't be shy and speak up. Of course, then colleagues, of course, can have the chance to ask questions to Paris.
Stanford, they implant people with questions ahead of the colloquia. And every time they're different ones so that the onus doesn't have to go to the same person every time. So then they are programmed, you will be the first one to ask a question, you will be the second one. So here we need volunteers.
Otherwise we can start from, yeah.
There you go.
She's not a student, but anyhow.
Okay, thanks very much for this nice colloquium. So I want to ask you, so since it has been discussed to have maybe a run at the Higgs pole mass at the FCC, so what's your personal takeaway from this? Do you think this might be worth it or not?
This is a programmatic issue. So the question is the following: whether to run the machine at an EE energy of 125 GeV spot on. Now, the width of the Higgs is only 4 MeV. So first of all, you would really have to achieve very, very high precision on the center of mass energy of the machine. It would have to be essentially monochromatic. There are some ideas on how to achieve it. It's challenging, probably possible. So that's the first thing. So it's not, pie in the sky. It would take 5 years to accumulate enough luminosity to see the Higgs little peak H2EE on top of the EE cross-section. What do we learn from it? We learn that atoms, the size of the atom is 1 over ME, okay? The parameter that gives you the size of the atom is the mass of the electron. 1 over ME is basically the Bohr radius. Everything else is 1, H bar, C, etc. So, is the Higgs responsible for the atoms and everything else that makes us in this? Is this an important question to answer? I would think very, very much so, unless there are even more burning questions that have come up in the meantime. And the hope is, with this type of precision, we will see deviations, right? Remember that what we learned from the W map compared to the Kobe picture in astrophysics. That's much nicer because it's visual and you see the precision. And actually, we measured the acoustic peaks, and we had, this expansion in spherical harmonics, and we measured the distance between, which gives us, all the stuff you've heard about, baryon acoustic oscillations and blah, blah, blah. So look at how much we learned from that precision. So maybe there's even more burning questions to answer by then. Otherwise, yeah, Higgs to EE would be a tremendous measurement to make. It would take 5 years extra.
Thanks.
I would have myself many questions, but as I said, I would prefer other to speak up. Aren't you?
I'm still a student, but I will not be around, presumably, by the end of this program.
What do you mean? We're all planning to be there.
But
Fabio.
I have just a curiosity. Why is the time scale of LEP3 longer than the time scale of SCCEE?
Because one needs to deinstall the LHC. One needs to take all the magnets out. One would have to start the deinstallation, you have to take it out from certain places. Now, near the experiments and so on, it's super hot, so you also have to wait some cooling time for it to, because otherwise, you send people down, they never come out again. So it would take, currently they speak of 6 years for the turnaround, whereas the other one is an independent tunnel, and the injector is actually a new injector, which starts from Prevesan and then eventually feeds into the FCCEE.
Okay, so again, another student.
Socrates said, "Girasko aidi daskomenos." Up until the end, we learn.
We are all students, in fact. Now, as you pointed out at the beginning of your nice presentation, by the way, thank you very much. It was really stimulating also presentation. The most sensitive, the most precise test of a standard model comes from low energy precision physics, the G-2 of the muon or of the electron. Now, my question is a bit related to this observation. Now, we are aiming here to improve the precision, and we are aiming in particular to a high mass new physics present beyond the standard model. On the other hand, there is a complementary, I emphasize, not in opposition, it is just a complementary, really a complementary sector which concerns high precision, low energy physics. And I think it is complementary in a true sense that you can get combined information from high energy and low energy precision physics, just in the search for beyond the standard model physics. So my question is whether the strategy, analogously to what, for instance, the US strategy, what is called the P5 plan, emphasizes the complementary role of high precision, low energy physics, so magnetic, electric, dipole moments, measurements of alpha electromagnetic, measurements of electroweak precision observables at low energy, running them to high energy, and so on. Because it might be reinforcing the high energy physics if one keeps also this complementary sector in full evidence, I think.
Thank you for the question. So the quick answer is the strategy very much supports the continuation of these specialized high intensity, high number, low energy experiments. At PSI, they're planning this incredible set of muon experiments and so on, MEG, mu to E gamma, and so on. These are fundamental measurements, extremely important. We should also remember one thing. We say very, very high precision, better than this from, say, G-2. But this that you see here is, to first order, it's the QED measurement. It's quantum electrodynamics, okay? With electroweak physics, we're nowhere near this level of precision, okay? We're planning to get, at the end of the LHC, the Higgs precision will be, for the best channels, at 2%. So it's, what LEP did for electroweak theory, what did LEP do for electroweak theory? It established it at the level of 10 to the minus 3, right? We had measurements with a precision of 10 to the minus 3. This is really the next frontier. So we should not, I mean, QED, we've known for a long time it's very, very precise. Now, once you enter this level of precision, you also have corrections from electroweak and so on. And if you had a very, very not so heavy chargino, it will also show up in the muon G minus 2. Sure, but we shouldn't think that they are orders of magnitude better here in terms of probing the new physics than the collider. It's a parallel path. The advantage of it is that the resources needed for it are far fewer, and they are proceeding, and you don't need 600 people, 260 contributions, and involving the equivalent of something like 1,500 people for a year to say, what should we do for this? Because this will be a once-in-a-lifetime type of decision. For the other experiments, there's lots of room. Do we support them? Absolutely. They're a key part. If you have time, I can show you the corresponding recommendations.
Yeah, more than a question, a comment from an experimentalist, because after 3 theorists, it's time for the experimentalists to speak up. And indeed, the detector maker more than just a, yeah. So, well, thank you a lot for the bright future that you have shown us, and also for highlighting that high luminosity LHC has still a lot to give. But I will even want to, for the young people, to stress it even more, because well, clearly there is space for ingenuity in the analysis, but sometimes you think that high lumi LHC is having higher luminosity, so having more statistics to use. Indeed, we profited a lot from the fact that we have to change the experiment to be able to stand the high luminosity, to put in a completely new experiment, essentially, with features that makes you able to widen the scope of what you can do just from the experimental point of view. Think of the tracking trigger that allows you then to have probably 40 megahertz trigger. Think to the high granularity calorimeter, the timing layer. They are all new things in experiment. They will widen up a lot the reach of the experiment on top of what the high luminosity will, just the luminosity will be able to give you, and immediately, not waiting for 2-3 times the luminosity you have now, but from the beginning, because you have a wider reach and wider scope. So there is a bright future for all our field, starting now and going to the time that you were discussing. So not only wait for 2046, but we can do very many things starting immediately as soon as we will have the end of the shutdown that is starting now. And also in terms of detector, will pave the way of new detectors for the future, with very important improvement that you are doing now. Just for the student to say, it's not something that will happen in the future, is happening continuously with a lot of promises and with a lot of very interesting things to do.
Thank you, Roberto. All I can say is that everything you said is correct. In fact, if anything, it's understated. There is really unprecedented new power to introduce into our reconstruction algorithms, into our measurements. These timing detectors, we will no longer have 3D reconstruction, we will have 4-dimensional reconstruct. We will have a time axis as well. The track trigger, to be able to find, so far triggering, which has been a nightmare in a Hadron Collider experiment. was always muons, electrons, jets. That's about it, the first level. Now we'll be able to have all the tracks, all the charged particle tracks at the full rate. This gentleman over here is working on reading out all the crossings with a level 1 so-called scouting trigger. Everything. This is, we used to say that we record a tiny, tiny, tiny fraction of the collisions, and now with the resolution of the level 1 trigger, we'll be looking at every collision at the high luminosity LHC. And let me break the news for you. We don't really know exactly how to do it. Technically, yes, the scheme is there, but then the question is, how do we apply to physics, what physics channels we go after, what measurements we can benefit, and so on? Lots of glorious space to cover, which is why I tried to indicate that, the strategy, concentrated on this whole issue of what you do next. Why? Well, because it takes 20 years to plan, to start building, and so on. It takes 20 years. Okay? So now is the time to plan that. But meanwhile, there is a tremendous amount of work to do. And it needs fresh minds.
Any fresh mind with a question?
Last question?
Fresh mind first.
Thank you very much for the nice talk. I was wondering, in the running plan you show for FCCE, there was a pretty defined schedule of Z, then W, then Higgs, and top. Now, of course, you're going to run the top lastly because you need the upgrade. But the first three, how defined is the running? And if so, what is the reason for running, for example, the Z before the Higgs or vice versa?
So, first of all, once you have the machine, you can decide in which order to run it, clearly. This is an indication. There's another plan whereby you go straight to the ZH, okay, and then you go back to the Z. The advantage of going to the Z is, first of all, you go to something that you know and love very much. It's important to have something that you understand well. The other thing is that this incredible precision will need incredible detectors. I haven't had time to cover that. But the detector, the systematic uncertainties that we will have to have in the FCCEE detectors will have to go down by huge factors with respect to today. That needs new detector technologies. In fact, people are looking at everything, including quantum technologies for calorimetry and so on, just to give you an example of a whole new frontier. I wish we had time to discuss it. Now, what that means is that these things will have to be calibrated. At the Z peak, you know exactly how to calibrate things, so it really prepares you for it. The good news is that it used to be that you had to change RF cavities as you moved along here. But now there's actually a new design for the radio frequency cavities and the use of the so-called RPO, the reverse phase operation, where instead of operating on the front of the wave, you operate on the back, okay? And that allows you with a single set of cavities, of 400 megahertz cavities, to run the entire first program. For the top, you cannot do it, you have to go to 800 megahertz. So there, you need to shut down and do the cavity change. So this is basically up to us to define. And if the high luminosity LHC starts showing interesting stuff here, flip it over, change it, okay? It's up to us.
Thank you, Paris, for a very fascinating presentation. I have a side question, maybe provocative, maybe no sense. As ICFA is also investing in the theory side, because I feel some lack of new ideas in theory somehow. You didn't, I mean, I don't know if it is in your commitment as chair of ICFA, because you are working in general standard scenario. But maybe it's also worth to invest some people, some effort in new generation theories. There are a lot of new people here. So, what do you think about that? Or I don't know if you have dealt with this issue.
There's two dimensions to the question. First of all, ECFA is really the Committee for Future Accelerators, and it's a committee that's advisory to CERN management and CERN Council. That's what it is. And its charge is to look at basically future facilities. Strictly speaking, we don't have anything to do with theory. But like I said, in theory, you know. So, now, we do country visits where we review the high energy physics program in all countries, and theory is always reviewed in that sense. Okay, and we make recommendations, typically always very, very positive. But that's about where ECFA finishes its job. Now, let's talk about theory at large. There is a tremendous amount of work to be done in order to get to the level of precision needed to match experiment. So, and if one looks at the techniques that have been developed in theory, for example, you know, this miracle of these multi-loop calculations for the Higgs, they're talking about N4LO, next to next to next to next to leading order calculation of the cross section. There are new techniques that have been developed and so on. There's a huge amount of work to be done. And this is for the precision. As for model building and phenomenology and so on, there's equally as much work to do. I could not be more enthusiastic about both sides of things, both the experiment and the theory. Do we need young theorists? Yes. Do we need young experimentalists? Yes.
Vado dallo studio.
Okay, thank you for your talk. My question was, since how you develop the strategy for colliders, and my question was around how do you incorporate the findings of the other fields? For example, this century will probably be impacted by gravitational waves and things like that, and searches like, as you said, the first phase transition, whether you see it or not with gravitational waves. How would that impact the runs? Would it impact the runs, the accelerator you plan to build or not?
Let me understand the question first of all, because I'm not sure I got it. You mean what's the interplay between this and gravitational wave physics?
Yeah. Yes.
Well, one has to connect them via some kind of model, first of all, right? If we find the, bipolarization in gravitational waves and so on, that will be a major discovery, and so on for inflation. We would still want to know everything that I presented here about the Higgs potential and the first order phase transition and so on, beyond questions of the ultimate, the inflation. Fabio can correct me if I'm wrong, but to first order, one doesn't preclude the other in any way whatsoever. Okay? Now, we do know from the cosmological measurements that, like I said, the critical index is slightly less than 1. It's excellent news. It means that inflation has a chance of being true and so on and so on. It doesn't change this part. Are there other connections?
Sorry. So, when you thought about this, around, did you just this?
I can't hear you. Sorry. You have.
sorry. So the question is really, how much do you base your planning exclusively on what you find at CERN and LHC, or with things maybe outside of collider physics?
Oh, no. We definitely, I hope I did not give you the wrong impression. This whole analysis is based on the assumption that in parallel to all of this, we will be investigating the neutrino sector, okay? The corresponding so-called PMNS matrix, which is the same thing as the mass mixing matrix in neutrinos that we currently know that we have in quarks, that we will get knowledge. The neutrino physics is fundamentally flavor physics, right? Neutrino mixing is at the end of the day the same as BB bar mixing, with the exception that here you really need, the little star that we put in neutrinos changing, that's basically new physics that we don't know how to put in there, okay? Completely new physics. Whether they are Majorana particles or non-Dirac and so on, no, all of that has been looked at. It's part of the strategy. It is a plan that's proceeding right now, and we have to pursue maximally. For example, leptogenesis. If we find enough CP violation in the neutrino sector, okay, that would indicate that, what we talked about earlier on about the baryon asymmetry and so on, and CP asymmetry, what you could do is that the leptogenesis could lead via the so-called Phaleron mechanism and so on into the corresponding 3 leptons can become 3 quarks and so on. So they're intertwined in theory right now. We need the experiment to indicate things, right? We need these things to happen. The neutrino experiments are there in 5 years from now, give or take. So it's all in the future. We are hoping that they will be connected. In theory, they are connected already, but it doesn't change the main thrust of the plan for a collider.
Okay, thank you.
Have I answered the question, or am I completely off?
Yes. No, that's...
I don't know whether the young person who asked the question is aware of the fact that this is the European strategy for particle physics. So this doesn't make any statement about the relevance, the importance of gravitational wave physics and experiments in gravitational waves. Just the planning of the future of the field in that sector for traditional reasons, organizational reasons, financial reasons, is done by other bodies than the European Committee for Future Accelerator. So I don't know whether this was relevant for the question asked.
I think the question was more on the side of whether we looked at the interplay with the other fields, if I understood the question correctly. And let me come here. The job of this strategy was the realization of the next CERN flagship project. I mean, the charter says that CERN has to have an accelerator, and that's how it advances. Gravitational waves are extremely important, but they're being pursued elsewhere. The strategy says we should continue the cooperation between CERN and high energy physics and the gravitational wave field at the current level, basically, if it's the organizational part.
So thanks for this very inspiring talk. It gives me another reason to blame for old age. But apart from that, I have a very trivial question. I was wondering, under the budget profile, if there was any discussion of having a site less expensive on the point of view of the geological challenge and the salaries, which in Switzerland are quite high, as an alternative for the FCC. Was this discussed by EFCA or not?
Well, first of all, it's not just ECFA here, this is a whole strategy process. Now, it wasn't really discussed, okay? The reason is that one of the challenges of building the corresponding collider in China is that they have to make a CERN next to it. And making a CERN is not an easy job. It's a big investment, and the human talent needed to build it is tremendous. So building it elsewhere in Europe would mean that one would have to build the corresponding lab. Now, one could be very visionary and say that in 30 years from now, everything will be remote, everything will be AI controlled and driven, and you no longer have shifters and in the main control room of the FCC, and an AI agent will be running and deciding when to drop the beam and blah, blah, blah. We haven't gotten to that level yet. That has not been discussed at all. Making a CERN is not an easy job. In fact, AI are trying to build the CERN for AI in Europe, and other fields are talking about making a CERN for XYZ, because they realize the power of this continuing organization and bringing in the international cooperation. The sum is much bigger than the individual parts.
Okay, I wouldn't profit too much of Paris because, I mean, we've been here for quite some time. But again, if there are some fresh mind that would like to ask a question, maybe we have a time for a last one.
Don't feel guilty because it's raining outside anyway, so
exactly. So it's not going to go anywhere. So.
One, yeah.
Over there.
So thank you for your talk. I was wondering if the FCC doesn't get approval, would that be worth for CERN building a minor machine, or would they prefer to make the alliance with China? I was wondering this.
Oh. I'm afraid we don't have enough physicists studying the physics of geopolitics, first of all. Therefore, and certainly I'm nowhere near well equipped to discuss the issue. I don't know. What we have said is that if it doesn't get approved, it will be because of a reason. So depending on what the reason is, then we investigate Plan C. Because one reason would be lack of money. Fine, but then in that case, we need a budget. One difference between the US P5 process and the European one is the US P5, they're given by the DOE, the Department of Energy, a specific budget in an optimistic scenario goes up, in a constant budget, just inflation, and in a pessimistic scenario where actually they lose resources, and they tell them, make a plan according to this. And they make a plan according to the optimistic one, of course. Okay? So, in our case, they say, do this, and now council will have to work back and forth in order to make it happen. Now, let me give you an example from the past. The LHC did not have enough money to be approved. What happened is that they put up a scheme whereby there would be the so-called missing magnets. Every third dipole would be missing. Now, this was a scheme that would not really work, okay? On the other hand, it got approved, and then with additional money from the US and other partners, the full LHC with all the full LHC with all the magnets became a reality. So, if it's money, it's one type of problem that you have to address. What's the other possibility? The tunnel. 90 kilometers at an average of 200 meters is non-trivial. And there's also lots of other issues to be, have to do with all the environmental studies and so on. The feasibility study has done a tremendous job in this. Already 1/3 of the excavation material they plan to implant with everything from microbes and so on to make it basically fertilized and reusable for agriculture, and so on and so on. But still challenges remain. So if it's a question of the tunnel, well, then you start looking at different solutions for the tunnel. If it's a question of money, we need a budget for the next iteration on this. So we'll see. But let's first try to get it approved. And if it gets approved, if you look at how much money it really is, over a range of something, it will run for 15 years, in 20 years from now. You do that, you do the math on that, you know, the amount of money per person, per physicist and so on. It's just the difference here is that we pile it all in one big number, the 15 billion. We don't just put it left and right. So 15 sounds like a big number. It is. And we should be grateful to society if they approve it. If not, let's find out what it can invest.
Thank you for this beautiful talk. I was curious about the expected timeline. If I'm not mistaken, this still needs to be approved from the CERN Council. So if this gets approved, I was curious just about the expected timeline, like projects and when the building will actually begin and so on and so forth.
So if it gets approved in 2028, okay, then 5 years later, plus there's a delta T of, currently what is running is, it was called the pre-TDR phase, okay? And with the clear message from the European strategy, it's now been renamed to the reference design completion, to be completed in 2028. We would like to have council approval in 28, maximum 29. After that, it takes 5 years to really commence the engineering works and so on. And from then on, it's straightforward if the funds are there, basically. How long does it take? A time scale between 2046 and 2048 for the start is what we're discussing right now, if we don't lose time. Yeah. I don't know if I answered, yeah.
Okay. Any other questions? Curiosities? Anything? Okay, so I think we can close the colloquium here. Let me thank Paris again. And see you soon in Padova.